Hello everybody. So in this lecture I'm going to follow the thermodynamic discussion. Last time we said we have two terms. One is delta H, which is equal to Q under constant pressure, and delta E is equal to Q under constant volume. We prefer to go with delta H because keeping the pressure constant is way easier than dealing with volume. And the way we keep the pressure constant, or we assume the pressure is constant, one way easy to do it is like just simply do the experiment open to the atmosphere. You can assume while you are doing the reaction, pressure will not change dramatically, and it will not, and it's not wrong assumption. And I said we have three methods to find delta H, or to find heat of one reaction. We started with the coffee cup calorimeter. We can use heat of any reaction is equal to minus Q of the solution or calorimeter, and Q of the solution you can get it through either C delta T, heat capacity multiplied delta T, or you can go with Q of the solution equal to MCS to delta T, specific heat capacity multiplied delta T. This time we do have idea about the mass of the solution. So if you do know mass of the solution, then you go with this one, with the second formula. But that case you need to have a specific heat capacity. So I do have the Q of the solution, so now I can calculate Q of the reaction, and we said the Q of the reaction. And if you have the Q of the reaction, and you can easily find delta H for one reaction per mole. So if you want to say delta H of any reaction either in joule or kilojoule per mole, you will use this formula. You go with Q of the reaction divided by number of mole of the limiting reagent, because heat is subject to mass. So if you have one that is limiting reagent, then you need to focus on it, because that one is going to limit you from either generating more heat or absorbing heat. So we divide by number of mole of the limiting reagent. And the next method that I showed you, I said you can use the Hess's law, and I did example about it. And in this lecture I'm going to go through some of them, and one example we can practice. We have here, we have three reactions that we do have the delta H for each reaction, and they are saying that do whatever you want to do with the first, second, third reaction and give us delta H of this one, the third reaction. So I said the way you treat Hess's law questions, you look to the reaction that you do not have delta H for it, and you underline the first reactant. Okay, the first reactant is carbon. I have it in only one reaction, so I'm gonna choose a reactant that I have it only in one reaction. I don't want it to be in two or more reactions, just one. Okay, how many mole do I have from this carbon? Only one. Okay, so I'm gonna say, let me find source of carbon, and I'm gonna find the source of carbon. It looks, this is the source for carbon. The second reaction, it has 1 mole carbon on the reactant side, so I'm gonna keep this one because I need 1 mole carbon on the reactant side. So I say, let's write the first one. Okay, sorry, this is the second reaction, I mean. Okay, so I'm gonna say this is the second reaction. delta H of the second reaction is minus 393.5 kilojoule over mole. Okay. Next, we go with sulfur reactant. Okay. We need 2 mole from sulfur. On the reactant side, find sulfur. First source, the only source for sulfur is the first reaction. And the first reaction here, it has sulfur on the reactant side, but only one. We need 2 of them. So what we need to do, we need to multiply this reaction by 2. Entire reaction by 2, including the delta H. So the first reaction, I'm going to multiply it by 2. I get 2 sulfur plus 2 oxygen, and then I get 2 SO2. Delta H of the first reaction is going to be minus 296.1 multiplied 2 unit kilojoule over mole. Okay, so we got this reaction. How about third compound? Third compound is a product. So you say product. What's the source for it? Is the third reaction. Third reaction, it has 1 mole from CS2, but on the reactant side. Excuse me. Only 1 mole on the reactant side, and I need 1 mole on the product. So I'm going to flip this one. Flip this reaction. So I'm going to say the third reaction, let's flip it. When we flip the reaction, we get CO2 plus 2 SO2, and then we get CS2 plus 3 mole of O2. What's happened with delta H of the third reaction? Because we flip the reaction, the sign here, it will be positive. So I say plus 1072 kilojoule over mole. Okay. So now, time to add these 3 reactions. Okay. We need to add these 3 reactions to generate this one, the given reaction. If you cannot generate this one through adding them, then somewhere you made a mistake. Okay. So I look to this one, I see carbon. Okay, I need carbon. Okay, next one, I do have O2, 1 O2 here, 2 O2 there, so 3 moles of O2, and I have 3 moles O2 also on the product side. So check this one. You have 1 mole here, you add it to the 2 mole, you get 3. 3 moles on the reactant side. Here we have 3 moles on the product side. If you have common compounds on cross of the arrows, then cross them. You cross them. Before you add them, just cancel them, because your life will be easier. You don't need to write all and then cancel them. Okay, so before I add them, I cancel the common compounds. How about CO2? I don't have CO2 inside this reaction, so I should not have it at the end. I have 1 CO2 on the reactant and 1 on the product side. I cross that one. Okay, what else? Okay. I see, okay, SO2, 2 SO2, so here, 2 SO2, okay, and 2 SO2 there. You cross those. And now we are left with carbon from first reaction plus 2 sulfur from the second reaction, nothing left from the reactant, and the product, we have only CS2 from the third reaction. How about delta H of this reaction? It will be delta H of the second reaction plus delta H of here first reaction plus delta H of the third reaction. So you apply them and you get the delta H for this reaction. So I'm gonna say delta H of the reaction is gonna be delta H of the second reaction. We got it now is minus 393.5 plus delta H of 1 is 2 multiply minus 296.1 plus 1072 unit for all kilojoule per mole. Let's calculate this one. So I see minus 393.5 plus 2 multiply 296.1. Okay, this one is minus, okay, minus 296.1. Minus 296.1. Okay, close it, plus 1072. Okay, so I got 86.3. 86.3. Let's double check it. So we have minus 393.5 plus 2 multiply minus 296.1 plus 1072 says 86.3. So delta H of the reaction 86.3. Okay. Yeah, it's gonna be okay because this is it's gonna be positive because that one was the biggest number. Okay, cool. So now we got the delta H for the reaction. Okay, and this one was the Hess's law. Okay, so now I'm gonna use the delta H of formation and practice that one to find delta H of different reactions. Okay. When it comes to standard delta H of formation, we said we need to have a reference. Okay, we need to have a reference, and we treat that reference, as a base. We set the delta H for it 0. We build compound from that, in a reference. If they have higher energy, it will be positive. Otherwise, it will be negative. For example, the most stable state for carbon is solid. For hydrogen, we know hydrogen, it cannot be just H. Hydrogen is H2. When we know hydrogen is gas. For chlorine, we know chlorine is dimer made of 2 elements and also is gas. How about nitrogen? Nitrogen is N2 and gas. For all of this, we say delta H. Standard delta H is going to be equal to 0. So all you go with 0. So I go 0, and same thing here, 0. But if you write N2 liquid this time, we can have liquid nitrogen. Delta H for N2, delta H of nitrogen when it's liquid is not going to be equal to 0, because this is not the most stable format of nitrogen. Nitrogen must be gas, okay, and this is liquid, and that's the reason delta H is not going to be equal to 0. And we have I put this sign, okay, and I keep saying this is the standard condition. I want to talk about the standard condition. What's the standard condition? Standard condition, if you're talking about a compound that is gas, if it's gas, pressure must be 1 atmosphere. If you have a compound that is solution, okay, so we're talking about solution. In that case, the concentration of a compound is going to be 1 mole over liter. Okay, and temperature must be 298 Kelvin or 25 degrees Celsius. Okay. Now we have standard delta H of formation. Say standard, this means standard delta H when you put the degree sign for it. When you put F subscript here, we call it standard and enthalpy of formation. Okay, so this is going to be standard enthalpy of formation because we have only one. Okay, enthalpy of formation. So you can raise this one and say enthalpy. Okay. Example, I go with C3H8. I know this compound is gas and we call it propane. I want to form this compound by using element of carbon and hydrogen. The most stable format of carbon is solid, and for hydrogen is H2 gas. You want to build C3H8, you go with C solid plus H2 gas. That one is going to give you C3H8 gas. Okay, balance the reaction, Sc3 carbon, so 3 carbon here, 8 hydrogen, I put 4. I started with 3 moles from carbon in a solid phase, and I added 4 mole of hydrogen gas molecules, and I got only 1 mole of propane gas. Because I did this reaction under standard condition, we call delta H of this reaction, we call it delta H of formation. Heat that you will either get or lose when you form 1 mole compound from standard under standard condition and from the most stable format of reactant. Okay. And delta H for this reaction is minus 4.7 kilojoule over mole. Meaning of this number, if I form 1 mole propane, I will get minus 104.7 kilojoule heat. Or when I get 104.7 kilojoule, that means I already formed 1 mole propane. Okay. Another one, you can see that you started with 3 moles of carbon and you got this number of heat. So you have the right to say, if I go with 3 moles of carbon, I should get minus 104.7 kilojoule or 104.7 kilojoule. Or when I get 104.7 kilojoule, that means I started with 3 mole carbon. You can do the same thing for hydrogen. You can use any of this fraction, okay, to do stoichiometry and predict how much heat you can generate or how much mass you need to use to get, for example, that amount of heat. And here's first example about it. We have 2 mole hydrogen gas plus 1 mole carbon gas, we get 1 mole CH4 gas. Delta H of this reaction is equal to minus 74.6 unit kilojoule over mole. The question is saying that if we start with mass of hydrogen 19.5 gram of hydrogen, how much heat we will get? Okay, how much heat we will get? We know if we start with 2 mole hydrogen gas, we will get minus 74.6 kilojoule heat. And the molar mass of hydrogen can go with 2 multiply 1.078, so it will be 2.0156 gram over mole. So this one is saying that if we start with 2 multiplied to 4 gram of hydrogen, we will get minus almost 75 kilojoule. Now they are saying if we go with 19.5 gram of hydrogen, how much heat we can get. Okay, so I go with this. How many or how much heat? And I go with 19.5 gram of hydrogen. I'll transfer it to mole divided by molar mass. Equal to 1 mole hydrogen. Okay, so now we got rid of a gram of hydrogen, we got mole of hydrogen. Next thing, use the mole ratio. Mole ratio says 2 to minus 74. So I'm gonna say if I go with 2 mole of hydrogen gas, I get minus 74.6 kilojoule. Okay, please be careful about this one. I wrote the minus here, okay, because I want to say it doesn't matter how much gram of hydrogen I start, I need to get the final answer negative, because the reaction, it has delta H that is negative. That means it's exothermic. So now whether you start with 1 gram, half a gram, or 0.1 gram, or 20 gram of hydrogen, you will get negative number at the end, because the delta H of the reaction is negative and the reaction is exothermic. Okay, so we have 19.5 divided by molar mass multiply 74.6 divided by 2. Okay, I got 360. Let's give it a try. 19.5 divided by 2.156 divided by 2 multiply 74.6. Okay, so the final answer says 3.61 multiply 10 to the power of minus the plus 2, and it's negative. The unit is kilojoule. I started with 3 sig fig, so I need to end it with 3 sig fig. Okay. So this is the way that you can use delta H of formation. Delta H of formation. This one is, it says I wrote the delta H of the reaction, okay, under standard condition, or you can simply call it delta H of formation. So you have the right to say here. Sorry about it. And so I'm going to write it down here. Delta H of the reaction under standard condition was minus 74.6 kilojoule over mole. I could write this one as delta H under standard condition, but delta H of formation is equal to minus 74.6 6 kilojoule over mole. Because the question gave me this one. Okay, so now we practice one question about using the delta H of formation, and I'm going to show you how to use them to predict delta H of one reaction. Okay. Have another question. It says you have 4 mole of iron plus 3 mole oxygen, you get 2 mole iron 3 oxide. They gave us the delta H of the reaction is negative. Because it's negative, so I'm going to say this is exothermic. Because it's negative. Now, the question is saying that how much iron is needed to release this amount of heat. Okay. Look to this one. It says to release. Because it says releasing, so your final answer here, this number must be negative. Okay. Whether they write this one, whether they say is releasing or absorbing. Okay. If they say it or not, frankly, you should not be worried about it. You should look to the delta H and judge about the sign of the heat based on delta H. Sign of heat always will be the same as sign of delta H. So you say sign for heat is going to be equal to sign of delta H. Delta H, sign for it, I'm talking about sign, not the amount. They will be the same, so let's not write, okay, let's not write equal. They will be the same. Delta H in this case is negative. So Q, it will be negative. Okay. Q, it will be negative. And I'm going to show you why you have to keep them, same sign. Okay. We go with this. We have 4 mole iron plus 3 moles oxygen. We get 2 mole iron 3 oxide. Delta H for this reaction, or delta H of formation, and is given and is equal to minus 1652 kilojoule over mole. Okay. Now they are saying we got heat. Okay, we got heat equal to 3.5 multiply 10 to the power of 4 joule. Okay. How did we get this heat? We had to add oxygen to iron to generate this compound. And based on this reaction, the balanced reaction, this is exothermic. So whether I start with 1 gram or 4 mole iron, I'm going to get heat. And because I'm going to get heat, sign of this heat must be negative. Okay. And I go with this. How many gram of iron I need to use to generate this amount of heat? So look to the sign, look to the unit. Unit of heat in this case is joule. It's not kilojoule. And unit of delta H is kilojoule. So I cannot connect the heat directly to delta H because they are coming with different units. So I'm going to transfer this one to kilojoule. And I go with 1000 joule equal to 1 kilojoule. Okay, so joule is gone. Now we have kilojoule. You go forward. Now time to use delta H. You will say this one. I have unit of kilojoule. So you will write the kilojoule there. Now you want to connect the kilojoule to mass of iron. Okay, to mass of iron. This number says whenever you get 1652 kilojoule, That means you started with 4 mole iron. So now kilo by kilo is gone, and we got mole of iron. Last thing that you need to do, you transfer mole to gram. You say 1 mole of iron multiply molar mass of iron, which is equal to 55.845 gram of iron. So I have 3.50 multiply 10 to the 4th. So this one will be multiplied 10 multiplied by 4 divided by 1652 multiply 0.845. I got 4.7, 4.73 gram of iron. Let's double check it. I got the same answer. Okay. So we have to use this amount of iron to get heat equal to 3.5 multiplied 10 to the 4th joule. Okay. And check this one. If you don't put negative sign in the front of heat, if you don't put this one, let's say you did not put this one, and you start with the given number, and they give you heat is positive, you use this one, now you transfer it to kilojoule, time to use delta H, and you transfer kilojoule to mole of iron to gram of iron. Your final answer, it will be negative because of the delta H. So you will have negative mass. Okay, mass, it will be negative. That's completely wrong. Mass cannot be negative. So somewhere we made a mistake. And that's the reason I say delta H must be, sorry, the heat of, my bad. Sign of heat must be the same as sign of delta H. If delta H is negative, then Q will be negative. If delta H is positive, Q, it will be positive. You want them to be same sign because they can cancel each other and you will get positive mass at the end. If delta H is positive, so you don't need to be worried about the Q because both of them are positive. Your final answer, it will be positive. Okay. So we got first part of the question. First part of the question is asking how much iron we need to use. How about oxygen? In this case, they did not talk about oxygen. That means oxygen is the one that we have excess from it. We have plenty from oxygen. So iron is the limiting reagent. They did not talk about oxygen, so assume we have excess of oxygen. Part B, it says, tell me how much heat we will get when we form this amount of iron 3 oxide. Okay. When we form 2 mole of iron 3 oxide, we get minus 1600 kilojoule. This one, it says if we form 8.75 gram. This is gram, this is not mole. So we need to transfer it to mole and see whether it's equal to 2 or not. If not, then we need to adjust it. Use the mole ratio. So I go with this. Have 4 mole of iron plus 3 mole O2. We get 2 mole iron 3 oxide, and delta H of this reaction, delta H for the reaction, is equal to minus 1652 kilojoule over mole. That means whenever we form 2 mole iron 3 oxide, we will get minus 1652 kilojoule heat. So you can treat this one as a mole ratio. Sorry, conversion factor. You can say 2 mole iron 3 oxide will give us 1652 kilojoule heat, or we get 1652 kilojoule heat if we form 2 mole iron 3 oxide. So now the question is saying mass of iron 3 oxide is equal to 8.75 gram. They gave you the mass. Now you need to transfer this one to mole and use the mole ratio with the heat and calculate how much heat you can generate. So I'm going to say how much heat we can get. If I start with if I form 8.75 gram of iron 3 oxide, I will transfer this one to mole. So I will divide it by molar mass is 159.69 gram of iron 3 oxide equal to 1 mole iron 3 oxide. Okay, you cancel gram by gram and you get mole. Use the ratio based on the balanced reaction. It says whenever you form 2 mole of iron 3 oxide, you will get minus 1652 kilojoule heat. And I use the delta H with the sign. So heat, it will be negative. We have 8.75 divided by molar mass multiply delta H and divide by 2. I have 45.3. Let's double check it. 8.75 divided by molar mass. Okay, so I got this one minus 45.3 kilojoule. Okay. Okay, so now we have part B of the question, and we know that we will get minus 45 kilojoule heat whenever we form 8.75 gram from the product, which is iron 3 oxide. This one is similar to the previous equation. Okay, I'm going to do one of them and leave the second part for you guys. So this one, it says find mass of titanium and iodine. Mass of titanium and iodine. If we get 1.55 multiplied 10 to the third kilojoule heat. Okay, so I'm going to go with the iodine. I'm trying to find how much mass of iodine we need to use to get this amount of heat. So I will say how much gram of I2. Okay, we need to find this one. You start with the given data. Given data is 1.55 multiplied 10 to the power of plus 3 kilojoule. You need to think about the sign of the heat. Heat in this case is 1.55 multiplied 10 to the third kilojoule. I said look to the delta H. If delta H is negative, then heat must be negative. Okay, you want them to be the same sign. So I go with negative for heat. Now time to use the delta H. We go with 839 kilojoule. We get this number if we start with 3 mole of iodine and 1 mole iodine equal to molar mass, which is 253.81, and unit is gram of I2. You can do the same thing for titanium. Just replace mole ratio. Mole ratio is going to be 2 this time, and you change the molar mass. Okay. We have 1.55 multiply 1000 divide by 839 multiply 3 multiply 253.81. Got it. 1406.7. So the answer is going to be 1.41 multiplied 10 to the power of third, and unit is going to be gram of I2. Okay. Kilojoule, yeah, is correct. Okay. Last thing about the delta H of formation is delta H. The meaning of delta H was the gap between reactant and product, energy of the reactant and product. Here. So this one is endothermic and this one is exothermic. In endothermic, we have reactant that they are sitting higher level of energy than so my bad. Okay, this one is going to be exo, so I'm going to change this one. My bad. Okay. And this one it will be endo. I have a reactant sitting higher level and the product, okay, or product, they are sitting lower level of energy than the reactant. We say the gap between reactant and the product, we call it delta H. So this one is going to be the delta H, which is equal to heat under constant pressure. How do we get this one? We say we have energy here, okay, and this one is coordination of reaction or a progress of reaction. The way you get the delta H is going to be heat, okay, or delta H of product minus delta H of the reactant. Okay. When it comes to endo, you have reactant sitting lower level of energy than the product, when we set the gap between reactant and product, we call it delta H. For exothermic, delta H is negative, so heat, it will be negative. For endothermic, delta H is positive, so heat, it will be positive. Okay. And again, delta H of the reaction, it will be delta H of product minus delta H of reactant. This one also is going to be the reaction. Now, if I use standard condition, I can say delta H of the reaction under standard condition is going to be equal to delta H of the product under standard condition minus delta H of the reactant under standard condition. You can do the same for this reaction, the endo, and I'm not going to do it. The formula is going to be the same. What if we have more than 1 mole from reactant and product? Let's assume we have this, A mole from A, and we got B mole from B. So delta H for this reaction, delta H for the reaction is going to be delta H of the reaction equal delta H of product. We have B mole from B, so it's going to be B multiplied delta H of product, which is B, minus A mole from A is the product, sorry, the reactant, and our reactant is A. So let's make it a general formula. The general formula in this case is going to be delta H reaction under standard condition is going to be equal to number of mole of product multiply delta H of the product minus number of mole of reactant multiply delta H of the reactant. We're going to use this formula to calculate delta H of any reaction under standard condition. Again, this is standard condition, so you cannot use this formula for non-standard condition. So there is a question here, and the question is saying that find delta H of this reaction. Find delta H of the reaction. We have the delta H for reactant and a product except O2. Delta H of O2 is not given. Okay. So I need to write this. Delta H of the reaction under standard condition is going to be equal to number of mole of product multiply delta H of the product under standard condition minus number of mole of reactant multiply delta H of the reactant under standard condition. So delta H of the reaction is going to be, those are the product, the right side of the equation, and the left side reactant. So I go with 4 mole multiply delta H of NO plus 6 mole multiply delta H of H2O minus 5 multiply delta H of O2 plus 4 multiply delta H of NH3, and we close it. So delta H of the reaction is going to be product. We have 4 multiply delta H of NO, replace the delta H of NO by the given data, and it's 91.3 plus 6 multiply delta H of H2O is minus 241.8, okay, minus 5 multiply. What's the delta H of O2? You look to O2. O2 is given in a gas phase. Delta H of O2 is going to be equal to 0. Okay, equal to 0. Delta H of O2, it will be equal to 0. Why? Because O is given in a gas phase. This is the most stable phase of oxygen. So we treat it as a reference. O2 gas is going to be the reference. Delta H for it, it will be equal to 0. So you multiply it by 0 plus, you have 4 multiply delta H of NH3, 45.9, and you close it. And unit for all, kilojoule over mole. So at the end, I will get have 4 multiply 91.3 plus 6 multiply 241.8 and plus 4 multiply 45.9. Got this one minus 902. Let's double check it. 4 multiply 91.3 minus 6 multiply 241.8 plus 4 multiply 45.9. Yes. So the final answer is minus 902. And unit is kilojoule over mole. Okay. So I showed you how to get delta H of one reaction by using a standard delta H of formation. You were given a standard delta H of formation for reactant and a product, and they were asking what's the delta H of this reaction. So delta H of the reaction is going to be delta H of product minus delta H of the reactant. But you have to multiply them by the coefficients, because heat is subject to mass or subject to number of moles. That's the reason I applied those, numbers. Okay. Next example. We do have a reaction. A reaction is equal. It says we have 4 mole from HNO3 gas plus 5 N2H4 gas. We get 7 mole of N2 gas plus 12 mole of H2O gas. Delta H for this reaction is given. Okay. So delta H of the reaction is equal to minus 31.47 kilojoule per mole. Okay, this is delta H of the reaction. Also, we have delta H for some of the reactant and the product. Delta H for this reactant is minus 133.9 kilojoule over mole. This compound, we are looking for it. N2 is not given. H2O is minus 285.8 kilojoule over mole. So the question is going to be, find delta H of N2H4. You are not given delta H of N2. Look to N2. N2 is given in a gas. This is the most stable phase of nitrogen. So I'm going to say delta H for N2 is going to be 0. I go with this. Delta H of the reaction is going to be equal to number of mole of product minus delta H of product, number of mole of product multiply delta H of product minus number of mole of reactant to delta H of the reactant. So delta H for reaction is going to be 7 multiplied delta H of N2 plus 12 multiplied delta H of H2O minus reactant, you have 4 multiplied delta H of HNO3 plus 5 multiplied delta H of N2H4. Replace number. Delta H of the reaction, we have it minus 3147 kilojoule over mole equal to, you have 7 multiplied 0 for N2 plus 12 multiply minus 285.8. Unit is kilojoule per mole, minus, we have 4 multiply minus 133.9, okay, plus, we'll write it down, plus, we can write it here, 5 multiply delta H of N2H4, and we don't have it. And I will close it. I will close it here. Okay. So I get minus 3147 kilojoule over mole equal to, first one, it's going to give me 12 multiplied to 185.5.8, sorry. This is going to be minus 3429.6 unit kilojoule over mole. Then we get minus to be plus. So 4 multiplied 133.9, 535.6 kilojoule over mole plus 5 multiplied delta H of N2H4. Okay. So I have the left side react, the right side I multiply those two. I wrote it here, and then minus to minus is positive, and here is positive. I wrote it, and I have 5 delta H of N2H4. Okay, so now I'll do the calculation, and so we have minus 3147 plus 3429.6 minus 535.6. This one is going to give me got minus 253. Sorry, here I forgot to, before I go, minus to minus 2 will be positive, minus to this one, it will be, this one is going to be negative. Sorry about that. So 253 kilojoule over mole equal to minus 5 delta H of N2H4. So delta H of N2H4 is going to be 253 divided by 5 kilojoule over mole divided by 5, and it's going to be 15.6 kilojoule over mole. Okay, so this is the delta H of N2H4. Again, why did I make this one negative? Because look to this one. Look to this one. We have minus of the reactant. So it will be minus of delta H of NH3, which is negative. It will be positive when you multiply it also by 4. And then minus of 5 delta H of N2H4. So it will be minus of 5 delta H of N2H4. Okay, that's the reason I wrote this one negative. Okay. So I'm done with this chapter, with the thermochemistry chapter. I hope my lectures were useful, and I need you to practice more questions from the worksheet that I'm going to post on Canvas. And also you will have a quiz on mastering chemistry. So give it a try and do your best. Have a good time. Bye.